Okay, good evening. I'm Andrew Lean, Dean of the College of Science and Engineering here at the University of Minnesota, and I would like to welcome you to the 15th annual Misel Family Lecture presented by the Fine Theoretical Physics Institute at the University of Minnesota. I will say, it is so good to see everybody here in person tonight. It's been a long time, 3 years, since the last time we were able to gather like this for a Misel lecture, so this is really very special. And you know, it's special because we get to share knowledge in person, which is much better, I think, for communicating it than in 2 dimensions. And that sharing of knowledge is really at the core of what we do as universities. So it's great to see you all come out for this. And also, we greatly appreciate the support from both the Misel family and from the Fine family supporting the university and that Theoretical Physics Institute, and for making an event like this possible. And I think we do have a couple of the Fine members of the family here somewhere. If we could just appreciate their support. I see, yep, there's Bob. I don't know where Bianca is. Oh, there she is. Thank you very much for all your support, really. Now, FTPI is a tremendous asset to physics at the global scale, and certainly to the University of Minnesota and the state of Minnesota. We take great pride in the accomplishments of the faculty and the researchers in the Institute. And lectures like this are very important because it enhances our community of learning by hearing ideas from leaders in the field, as we will shortly, as well as sharing our leading ideas here at the University of Minnesota with those same leaders throughout their visit and time here in the Twin Cities. I particularly appreciate the international flavor of the lecture, since it enables knowledge sharing across national boundaries. And we all know that science really knows no boundaries. And so I think this is an excellent example of that. Public lectures such as this are also critical because they make the ideas of science and engineering accessible to a broad audience. It is through this interaction that we can share our passion for learning and spark that interest in many of those for whom science may not be a daily interest. And that's a key part of our mission at the University of Minnesota as a land-grant university, where we push the boundaries of understanding, but also make sure that understanding is then delivered to the public that we serve. Now, I'd like to now introduce the director of the FTPI, Alex Kamenev, who's going to introduce tonight's speakers. Alex?
Thank you, Andrea. Wow, it's a full audience. We were extremely nervous that coming out of COVID, we will not be able to fill the room, but apparently people are still here. So I'm so glad that we are transitioning from social distancing to social interactions, finally. I'm extremely excited to see so many familiar faces in this room and even much more new faces. And we very much hope that you and your family and your friends will keep coming to the Misel events. We're going to run them every year. And we will try at the Fine Institute to bring best of the best, creme de la creme of modern science, to tell you what happens at frontiers of physics, astronomy, cosmology, and so on. So our today's speaker, Professor Carlos Frenk, totally fits this bill. He was born in Mexico, and as he said in one of his lectures, it was a beautiful view of Mexican night sky, which made him think how stars came into the being, and eventually led him to be a cosmologist. So he entered a National Autonomous University at Mexico City and graduated from it with a degree in physics, and then continued to Cambridge, where he acquired his master's and PhD in astronomy. His postdoctoral studies were mostly in California, in Berkeley and Santa Barbara. And since 1986, he joined the third oldest university in England, which I'm sure everybody knows what it is. Here is a clue. It's a Durham University, and he refers to it, at least I think he refers to it, as being the center of the universe. Is it true? Yes. So no surprise that Carlos remained there ever since. Since 2001, he became an Ogden Professor of Fundamental Science and founding director of Institute for Computational Cosmology. And he led this institution for 20 years. And during this time, he received numerous awards and recognitions. To name a few, he was named a Fellow of the Royal Society. Let me see my list. What else? He received Royal Society Wolfson Research Merit Award, Gruber Prize in Cosmology 2011, Dirac Medal 2020, Rumford Medal 2021, and many, many others. His achievements in science, however, are by far more numerous. And I couldn't be possible do any justice to them trying to convey to you in few minutes I have here. So therefore, without further ado, ladies and gentlemen, please welcome Professor Carlos Frenk.
Thank you, Alex, for the very nice introduction. I'm glad you stopped because I was beginning to look forward to my own talk, which is never a good thing to do. So before I start, I'd just like to say how pleased I am to be here and how grateful I am to Bianca Fine and to the Misel family for giving me the opportunity to speak here in Minneapolis, which happens to be a city very close to my heart. And the reason for that is very simple. My grandson was born here 5 years ago. So it's a place that, as I say, occupies a very special place in my heart. Now, so let me now get to the business of the universe. So this lecture, as the title indicates, has to do with the universe. And hold on, I have a way to change my slides, which I just need to turn on. Right, so well, I had a way to change the slides, but I think this froze because it's been sitting there for too long. Not as long as that cathedral that you can see there. Let me restart this again. Something's not right. Okay. We're going to have to start again in a minute. So why does this not? Okay, I'm going to try the well-tested remedy, which is to reboot. It just froze. I think it's been sitting there for too long. It might just be oh, is that, you think?
No, something's moving.
Oh, good. Oh, right. All right. Okay, thank you very much. Yes, I should say that my institute has one of the largest supercomputers in the United Kingdom. And as one of my students pointed out to me, you run one of the biggest supercomputers in the world, and you cannot even change a slide in your presentation. So anyway, so the title of this talk is How Our Universe Was Made, and the subtitle is All from Nothing. Now, all, of course, stands for the universe, and as I go along, I will tell you what I mean by nothing. You will see that nothing in physics is actually something quite interesting. Now, of course, this is a lecture on cosmology, on the science of the universe, And cosmology is one of the oldest sciences, and it asks some of the most fundamental questions that humans have asked. Questions such as, how did our universe begin? What is it made of? How did it evolve to its present state? And what does the future hold? So these are the questions that cosmologists grapple with in their everyday life. And of course, it's not just us cosmologists who worry about these things. These are questions that interest not only cosmologists, but people in many other disciplines, theologians, philosophers, artists, many, and the ordinary public ponder about at least some of these questions. And these questions go back a long time. I would say even that maybe you can define the beginning of civilization as the time where our ancestors started pondering about the universe. But what makes my discipline, cosmology and physics, unique is that we have a very well-defined way to try to tackle these profound questions, and that is based on the laws of physics. And that's what distinguishes us from philosophers, theologians, and so on. Is the sound okay, or is the sound a bit too loud? Is it okay? Yeah, all right. So this is what makes cosmology distinct, say, from theology or philosophy. We have a methodology that's been developed throughout the centuries based on the laws of physics. Now, I'm sure the laws of physics are just general rules about natural phenomena. For the most part, they are derived empirically through experimentation and observation in the laboratory. I once said all laws of physics are derived like that, and then a member of the public said, no, that's not true. General relativity, that came out of Einstein's head, not out of any experiment. I think that is true, and that's probably the exception. All the other laws of physics are derived by observation and experiment. Then they're expressed in this wonderful language of mathematics that allows us to manipulate them and then explore their consequences. So well-known laws of physics, you can see there, Newton's law of gravitation, Bohr's gas laws, quantum mechanics, relativity. These are the laws of physics. And they are experimentally verified on Earth. But one of the greatest mysteries, and in my mind, the greatest mystery of cosmology, is the fact that these laws appear to be universal, meaning that we discover them here on Earth, and yet they seem to apply everywhere and at all times in our universe in conditions like the Big Bang that bear no resemblance at all with conditions in the laboratory. So why are the laws of physics that we humans can uncover, why do they work so well everywhere in the universe? So to me, that is a very, very profound mystery. And it has a question mark. I really do not know the answer to the universality of the laws of physics, but of course it gives us a very powerful methodology to try and tackle some of the questions that I mentioned earlier. Now, so the building blocks of the universe are galaxies. It's a picture of a particularly attractive galaxy. These are collections of up to 100 billion stars. And we are today located here, 2/3 of the way from the center of the Milky Way. And as Alex says, my institute is just in the middle of this picture. Now, just to get you in the right cosmic mood, I'm going to ask Tony to turn the lights down. And I want to show you a movie made by a colleague in Hawaii, Brent Tolley, which is a movie of what we have around in our cosmic neighborhood. So it is a journey through our cosmic environment, and you will see everything you will see in this movie is actually out there. It's based on real data. Now, is this movie going to play? There he goes. So this movie was made, as I say, from real data by Brent Tolley, and here we go. We travel, first of all, towards the constellation of Orion that you can see out there. Many of you would recognize it. And next to the constellation of Orion, there's this cloud of gas and dust called the Orion Nebula. And this is a place where new stars are being formed. So in the Milky Way galaxy, there's about every year there's a new star being born. Here's another example called the Horsehead Nebula. Again, it's a place where new stars are being born. Now, in fact, actually, stars tend to be born in groups. Here's something called the Carina Nebula, and if you look closely enough, you see there are 6 or 7 stars being born together from this cloud of gas and dust. Now, however, not all gas clouds are nurseries of stars. There are others, like the one we're about to see here, called the Crab Nebula. This is a graveyard of a star, not unlike the sun, that ran out of nuclear fuel and then blew up and ejected the outer parts, producing something called, has a strange name, a planetary nebula. Stars shine because they have nuclear reactors in the center, and of course, eventually, they run out of nuclear fuel, and they end up like, in this case, the Crab Nebula. Now here is the only bit of artistic impression. Here, obviously, we cannot look at our Milky Way from outside. It's a galaxy very similar to the Milky Way. Galaxies like this one are about 30,000 light years across. It takes 30,000 years for light to go from one end of the galaxy to another. Now we're going to look at our nearest neighbor called the Andromeda Galaxy, which is about 2 million light years away. It has a companion called M32, which itself has its own clouds of gas and dust, where new stars are being born roughly at the same rate of 1 new star per year. Eventually, we're going to finish our journey here on the left in something called the galaxy cluster, which is a collection of galaxies. But before that, we'll just take a little detour to admire some of these wonderful things that nature has managed to produce, these so-called grand design spiral galaxies, and some, like this one, coming into view, interacting with a neighbor. And the universe is full of those. Now, as you can see, galaxies are not distributed at random in the universe. They make these patterns called the cosmic web, which, as I will show later, tell us a lot about the beginning of the universe. But we're going to end our journey in the Virgo cluster of galaxies, which is about 30 million light years away. And this is a collection of galaxies, a few hundred bright galaxies in the center. There's a very famous galaxy called M87. And one reason this is so famous is because at the center of M87, there's something that we call the supermassive black hole. It's a black hole which weighs about 1 billion times as much as the sun. And it's producing you saw a little jet quickly there, which is a result of the digestion of all the material around this black hole by this galaxy. So that's what our cosmic neighborhood looks like. So physicists like to count things. We want to be quantitative. And one of the first questions you might ask is, how many galaxies are there? Well, we can count them with surveys of galaxies, and it turns out, interestingly, that the universe has about 100 billion, the visible universe, that is, as far out as we can see, there are about 100 billion 100 billion galaxies, which coincidentally is about the same as the number of stars in the Milky Way. So it's 100 billion stars in the Milky Way, and there's 100 billion Milky Ways in the visible universe. So I was talking to Bianca at dinner, and she trained as a molecular biologist, and she was saying to me, oh, the Big Bang, all these things that are just so complicated. And I said, no, this is not complicated. The universe is very large, for sure, or alternatively, we're very small compared to the scales of the universe, but the universe is simple. It may be big, but it's simple. And of course, it's not size, but complexity that makes things difficult to understand. So the objects that she used to study when she was a scientist, for example, humans, they're much smaller than a galaxy, but they're a lot more complex. And so that's one of the reasons why I think physicists have a much easier time in their science than do biologists and psychologists. Nevertheless, in spite of the huge number of stars in the universe, one of the big surprises of science of the last 20 years or so is that all the stars and all the galaxies in the universe make only about 5% of what the universe contains. So stars are made of atoms, the atoms that we learn about at school in the periodic table of the elements, and all together, all these galaxies and all these stars make only about 5% of what the universe contains. That's normal matter makes 5%. About 25% of the dark matter, of the mass of the universe, is not made of ordinary atoms, and it doesn't shine. Something that we call dark matter, I'm going to tell you a lot more about dark matter, it is just matter that is just invisible. It doesn't shine at any wavelength of the electromagnetic spectrum, and it makes most of the matter in the universe. But the lion's share of the universe is something even more mysterious, something called dark energy, which makes up about 70% of what the universe contains. Now, dark energy was discovered only at the turn of the last century, and we know very little about dark energy, but we know what it's doing to our universe. So I will show you in a minute, and I'm sure you all know, the universe is expanding. That's what we mean by the Big Bang. But not only is it expanding, the rate at which it's expanding is getting faster and faster and faster. So the expansion of the universe is accelerating as though there is something pushing the universe and causing it to expand ever faster. And that is what we call dark energy. It's this mysterious form of energy which opposes gravity and is causing the cosmic expansion to accelerate. And it makes up the lion's share of the contents of our universe. Whenever in science you come across some strange sounding concept like dark energy, the first thing you should be is very suspicious and say the physicists behind this don't understand a word about it. That's why they give it a name as magical and mystical as dark energy. In fact, by the end of this lecture, you will know about as much about dark energy as the professionals do, and it will take me one slide to explain dark energy. Now, but both 95% of our universe are still questions that are very much mysteries, particularly the dark energy. As I will show you, we know a lot more about dark matter than we do about dark energy. So what about dark energy? Well, I mentioned the cosmic expansion. The cosmic expansion was discovered now nearly 100 years ago by this man, Edwin Hubble, of Hubble telescope fame. And the days you can see him here in Chicago when physicists were allowed to smoke in their offices. I can tell you how long ago this was. Now Hubble, or rather his assistant, Cypher, measured distances to nearby galaxies and measured also the velocities of these galaxies. And they found a huge surprise. All galaxies around us seem to be moving away from us with a speed that increases in proportion to their distance. That's that plot there, which is a very famous graph in physics. So all galaxies are moving away. The farther away they are, the faster they move away from us, and that means the universe is expanding. Now you might say, well, what's wrong with us? Why are all galaxies moving away from us? Well, there's nothing special about us. Any other observer anywhere else in the universe would see exactly the same phenomenon. That's a property of an expansion of the sort where the velocities increase in proportion to the distances. So if you're sitting in any of the galaxies we saw earlier, Andromeda or any other galaxy in the universe, you will see exactly the same phenomenon, every other galaxy moving away from you, just like if you inflate a balloon and you put dots on it before you inflate it. As you inflate the balloon, all dots seem to be moving away from all other dots. So the expansion of the universe is nothing particular. We're not at the center of the universe. It's a universal phenomenon. And we've known this for about 100 years, and people in the bars talk about the expansion of the universe. Now, what came as a big surprise towards the end of the last millennium, studying distant supernovae, is the fact that astronomers were able to measure the rate at which this expansion is happening. And that's when they discovered that the expansion is accelerating. Now, this came as a huge shock. The reason is simple. Before these measurements, we thought that the expansion should be slowing down because we know for sure the universe contains matter, and matter produces gravity. As people like to say in the US, gravity sucks, meaning it sucks things And so if the universe started with a Big Bang explosion, gravity should be trying to bring back matter and should be slowing down the rate of expansion of the universe. And what was measured was exactly the opposite. The universe seems to have some mysterious force that's pushing against gravity, accelerating the expansion of our universe, and that is what we refer to as dark energy. And even though we don't know much, not much, I'll show you all we know in the next slide about dark energy, that discovery was enough to earn the Nobel Prize in Physics in 2011 to three colleagues, Sol Perlmutter, Rees, what's his first name? I just forgot his first name now. Yes, anyway, the names don't matter. The point is that the Nobel Prize was given for the discovery, and Brian Schmidt is the other one. Adam Rees, Brian Schmidt, and Sol Perlmutter. So the reason I forget them is because I taught them when they were young, and it's kind of slightly weird when people you taught start getting the Nobel Prize. But anyway, so this was certainly worthy of a Nobel Prize, the discovery that the expansion of the universe is something completely unexpected. So what is it? What is the dark energy? Well, the answer is we don't have a clue. We think, well, first of all, we do know the effect, which is something that produces a repulsive force, sort of anti-gravity, that's causing the universal expansion to accelerate. Now, most of the universe is completely empty. Not here, of course, but even in the galaxy, the space between the stars is pretty much empty. But between the galaxies, there really is nothing. It's completely empty. It's what we call a vacuum. So the galaxies are little islands in the sea of vacuum. And so whatever it is that's pushing the galaxies must have to do with the vacuum. So that's about all we know about dark energy. It is some form of energy whose origin is mysterious and who's likely to be associated with a vacuum, with empty space. Now, all of you know as much as the professionals who earn a salary trying to understand dark energy. This is really, I think, that people here in the audience who know a lot about dark energy, and I hope they will agree with me that it's a nice summary of that subject. Now, so let me now tell you about something that I spent my whole life studying, and something we know a lot more about. Even though we don't know what it is, we have some pretty good hints of what it might be, and that is dark matter. Now, so we can see it. Dark matter, as I said, is dark. So how do we know it's there? Well, we know it's there thanks to the magic of physics. And in fact, in this case, it's very simple physics. It's physics that are 350 years old. Goes back to that man over there, Isaac Newton, who discovered gravity. So Isaac Newton's great discovery, which is in fact permeates all of modern life. We may not realize this, but when you get on an airplane, you're making use of Newton's law. That's why airplanes, that we know how to build airplanes. Even when you build a building like this, it's all back, because there are forces involved, there's gravity, and there's Newton behind that. So Newton realized that matter produces gravity, and gravity produces motion. So if you can measure the way things move, for example, the way the planets move around the sun, then you know you can then go back and figure out what matter, how much matter there is. And that's the reason why Newton got hit by an apple, because the gravity of the Earth produced a motion of the apple that hit him on the head. So it's very simple physics, and when you hear the equations, and the very, very simple equations, and when you use Newton's laws to understand the way in which the stars in galaxies go round and round the center, then you come up with a big surprise. So astronomers are very good at measuring velocities, and they can measure how rapidly the stars are going around the center of the galaxy, Milky Way, or any other galaxy. We move at about 200 kilometers per second around the center of our Milky Way. So you can apply these basic principles, and you find a big surprise. You come up short when you say, well, how much matter do I need to account for the velocities of stars? You come up with a number. How much matter do I see in the form of stars and gas clouds? And you see 10 times less than you need to account for the rotation of the stars. So the stars are rotating too fast to be held in place by the gravity of the mass that you can see. Well, it follows then, because the galaxies are not blowing themselves apart, that there must be something you cannot see that's holding the galaxy together, and that is what we call dark matter. Just a few years ago, I was in London walking around, wondering about some subtlety to do with this. I was really, really lucky. I ran into Isaac Newton in his modern incarnation, and there he is. I mean, he's the same. The hair is the same, the nose is the same. So it is an incarnation of Isaac Newton, who he decided that physics was a little bit too complicated with all this dark energy and stuff. He decided to become a musician instead. Actually, I don't know if everybody still recognizes this man. So when I give lectures to younger people, they don't know who Brian May is. And anyway, for those of you who don't know who he is, it's called Brian May. He was in a band called Queen, and he's a brilliant musician. But he's also an astronomer. He's got a PhD in astronomy. I know him because of his astronomy, not because of his music. At any rate, that then, the way in which we should think of galaxies, is as little pools of light in the center of enormous clumps of invisible dark matter, which astronomers, for a reason I never fully understood, we call them halos. They're not really halos. It must be because we have some saintly inclinations in astronomy. They're actually clumps of dark matter, and the galaxies are sitting in the middle, held in place by gravity. Now, some of you might say, well, you know, sure, but that argument is a little bit indirect. Do you have a better card to play? Well, I do, and that is the following. Look at this picture taken by the Hubble Space Telescope. What you see there is a galaxy cluster, like the galaxy cluster we saw in the movie. Let me see if I can get this mouse here to work. Oh, look at this. No, wait a minute. I can make that arrow big if I go here. Right there. So you see galaxies, normal galaxies like these ones. So these are just ordinary normal galaxies. But then you see also these very strange looking objects, these arc-like features. There's one there, they're all over the place. So these are very strange arcs. Now, what are these? Well, these are also galaxies, but they're not in the cluster. They're a long way behind the cluster. And the light of these galaxies, as it comes towards us and encounters the cluster, gets deflected by the gravity of the galaxy cluster. So that's what E equals mc squared means. It means that E, which is light, knows about m, which is mass. So the mass of the cluster is causing the light from the background galaxy to be deflected. And you all know, just from looking at a spoon in a glass of water, that the minute you start fiddling with the way in which light travels, then images get distorted. And in this case, they get distorted into these arc-like features that were so dramatically discovered by the Hubble Space Telescope. Now, this is a phenomenon that goes back to the great Albert Einstein, who explained it in a letter in 1919, I think it is. You can see these are the days when science was done by people writing letters to their friends. So the letter says, "Dear colleague," it's in German, so I won't read it for you, but you see there the phenomenon they're talking about, a light ray that encounters the gravity, in this case of a star, and gets deflected. And that deflection distorts the image of the galaxy. So here's a little experiment which we did in my institute. What you see here is a picture taken by the Hubble Space Telescope of this is the deepest picture humans have ever made. Not even the JWST has yet made, to my knowledge, a picture as deep as this. So many of the objects you see there are, especially the small ones, they're so distant that the light has taken most of the age of the universe to get to us. But I'm going to use this picture, this very famous picture, as a tapestry, as a background. And we're going to do an experiment, a thought experiment, where we have this background of very distant galaxies, and in the foreground, we're going to grow a lump of dark matter, and you're going to see what that does to the images of the background galaxy. So what we're doing here then is essentially seeing how light travels and how it, solving Einstein's equations and seeing how light gets deflected and the images distorted. So there. Oops, sorry. So there you see, so here's this blob of dark matter that we're artificially growing in a computer, getting bigger and bigger and bigger, and causing this distortion of the tapestry of background galaxies from the Hubble Space Telescope. So you see exactly the same phenomenon, exaggerated a bit here, where the light of these background galaxies becomes distorted. So we understand exactly why we see the picture in the Hubble Space Telescope, and moreover, we can now ask the question, well, how much matter does the galaxy cluster need to have in order to produce these distortions? And when you do that calculation, you find that you need 10 times more matter than what you can see in the shape of the stars, you can see in the galaxies that you see there. So the galaxies contribute only about 10%, a tenth of what you need, the total amount of mass you need in order to explain these arc-like features. So this is, as people like to say in this country, in Europe, we don't like this language, but this is a smoking gun of dark matter, and because it is really the only way to understand why light is deflected like this, and it is the fact that we can measure exactly how much dark matter this cluster has to have, and it's roughly 10 times more than what we can see in the form of galaxies. So what is the dark matter? Well, we know it's there. There's no question. The evidence is overwhelming. Question is, what is it? Now, we don't know for sure yet, because it has not yet, as I will show you in a minute, been discovered in the laboratory, but we have a pretty good idea. And for that, I need to go to a picture for Bianca about the dark matter, about the Big Bang. Here's the Big Bang illustrated for you. And the moment of the bang is there on the left, where you see the yellow image, and then time goes from the left to the right until the present. There are various landmark events in the life of the universe illustrated here, all the way to the present, where we know the universe is 13.7 billion years old. Now, the dark matter, we think, was formed very early in the life of the universe, when it was just a tiny fraction of a second, when the universe had cooled enough that these particles of what is dark matter today were created. So these are elementary particles that do not interact with anything else, or not very strongly, and that's why they're dark. In order for light to be produced, you need things to interact strongly, particles to interact. These ones interact so weakly that they essentially just remain dark. So the current view of what the dark matter is some elementary particle created very soon, a tiny fraction of a second after the Big Bang, and the best candidates go by the generic name of cold dark matter. Now, so of course, we have this very compelling astronomical evidence for dark matter, but if it is a particle, you really would like to be able to capture one of these particles in the laboratory. And there are, in fact, efforts to search for dark matter. This is experimental physics, like they do here in the university. And I don't know if you've ever met an experimental physicist. I know there are a few here, so I'll show you what you want to spot them. This is what they look like. And a subset of experimental physicists are busy trying to discover these tiny elementary particles that were created soon after the Big Bang. Now, these experiments are difficult for the obvious reason. These particles don't interact. So how are you going to catch it if that's why they're dark? If you make a detector, they just go through the detector and don't interact. So, of course, it's extremely hard. And now, when I say they don't interact, this is only a statistical statement. If you wait long enough, you'll get one of these particles, gets You get lucky and it hits an atom on the detector, and then the atom might move a little bit, and that is the signal that many people are trying to find. There are many experiments across the world. There's one of the most advanced ones in Canada, in a mine here in Sudbury. You need to have these experiments done on the ground because the Earth is bombarded continuously by all sorts of debris from outer space called cosmic rays. And the people here who study cosmic rays are not going to like it that I call it debris, but from our point of view of experimental dark matter researchers, they are debris. So that's why the experiments take place in mines, like this one in Ontario, and there is also a very advanced experiment called PANDA in China. Here's a picture from their experiment. So experiments all over the world, and no dark matter has been detected yet. But I'm hoping one of these days I'll wake up in the morning and read the newspaper and it says the dark matter was finally detected. So we have to be patient because the experiment really is very, very difficult. So just to summarize what I've told you so far, 5% of what the universe contains is dark matter, 25% is dark matter, an elementary particle from the Big Bang, and then the evidence comes from the velocities of stars in galaxies, from this phenomenon of gravitational lensing, and then we don't know what it is for sure because the particle hasn't been discovered, but we think it should be an elementary particle. And I think it should be discovered very soon. I would say within the next 5 years. The problem is I've been saying that for the last 20, but I think this time I'm right, that the experiments are now immensely sophisticated. Then the lion's share of the universe is dark energy, and we know it's there because of the accelerated expansion of the universe. We really don't know what it is, but we do know that whatever it is, it must be associated with the vacuum. So that's a summary of what I told you so far. And I want to focus on a simple question. Why have I and many other people spent all their careers trying to understand dark matter? Sure, you want to know what the universe is made of. Yes, of course, but that's only part of the answer. The reason is that without the dark matter, I wouldn't be here talking to you. And because the dark matter is the agent that's responsible for everything we see in the universe. That wonderful tour we did at the beginning that you showed I showed all these magnificent galaxies, all that would not be here without dark matter. So let me explain to you how that works. So for that, I need to tell you about the origin of galaxies in the universe and how dark matter, its gravity, is what causes a structure like galaxies and other cosmic structures to form. So now let me tell you a little bit about that. Where do galaxies come from? And the answer here is good for those of you who don't know it already. It's a shock, and I hope you'll be as shocked as I was when I first came across these ideas some years ago. So here we go back to the Big Bang. And now the story begins very, very soon after the Bang. In fact, a fraction of a second after the Big Bang. Decimal point, 34 zeros and 1. In the language of physics, we call this 10 to the minus 35 seconds. That's when the story of the origin of the universe as we understand it today begins. That's the earliest time at which physicists can talk about phenomena and still keep a straight face. We don't know what happened before that for reasons that we can discuss later if you're interested. Now, here I will now explain to you in a minute what I mean by the title of my talk. I'm going to now tell you what I mean by nothing. And you will see when the title was All from Nothing, how nothing became everything. So let me just tell you a little bit about that. So the story begins 10 to the minus 35 seconds after the Big Bang, where we believe, and we have evidence that I will show you in a minute, that the universe wasn't born quite right. So when the universe came into existence, it was not in a perfectly stable equilibrium state. It had an excess of energy, not dissimilar from the dark energy. It had too much vacuum energy. And the universe got rid of that vacuum energy by expanding very quickly over a very brief period of time. So this now goes by the name of cosmic inflation, which was discovered by a previous Misel lecturer, Andre Linde, but not discovered. He was postulated. He did the theory together with Alan Guth at MIT. And Alexei Starobinsky in Moscow. So the idea is that the universe was slightly unstable when it was born, and it became stable, if you like, by shaking off this excess energy, by expanding very rapidly, such that it went from being the size of a needle to the size of a soccer ball in this tiny fraction of a second. This is the hardest part of this lecture. Actually, the hardest part is about to come. So this phenomena of inflation is associated with what we call quantum fields. So quantum fields, quantum physics is the physics of the subatomic world, and many of you would, I'm sure most of you are not nuclear physicists, but maybe many of you realize that when we talk about the quantum world, we talk about uncertainty, about things that are fluctuating all the time. So in the quantum world, nothing is really quite predictable. Everything fluctuates. These are called quantum fluctuations. And when the universe inflated, this inflation was produced by a quantum field that produced quantum fluctuations. I have an illustration here of a quantum fluctuation. So this is the best I could do. Whoops. Come on. Here we go. Let me see. There. Can you see that fluctuating world? This is what quantum physics is all about. So for those of you who know a little bit more than average, what you see in that picture is matter and antimatter. In the vacuum, and that's why physicists are enamored of the vacuum, all sorts of strange things happen. In particular, matter and antimatter produced out of nothing, something called the Heisenberg uncertainty principle, and then these matter and antimatter encounter one another, and they annihilate into energy, and then the energy decays into matter and antimatter, and these fluctuations are going on and on and on. They're called quantum fluctuations, and we study them in the laboratory every day. However, if these quantum fluctuations happen when the universe is expanding very rapidly, they get stretched. And when they get stretched, they're no longer quantum things, and they become imprinted as genuine ripples or fluctuations in the density of the universe at this very early time. So I say this is the hardest part of this lecture. I'm going to say it one more time. I don't expect those of you who are not physicists to understand fully what I'm talking about. I just want you to get the flavor that when the universe came into existence, there was a vacuum, and in physics, the vacuum is not empty, it's full of fluctuations. These fluctuations have to do with a very famous physicist called Heisenberg, the Heisenberg uncertainty principle, and it is these quantum fluctuations that grow to become real fluctuations in the energy density of the universe, and the proposition of modern cosmology is that this is where galaxies come from. Right, so let me repeat. So the idea is that a big galaxy with 100 billion stars started life 10 to the minus 35 seconds after the Big Bang as a small fluctuation of the vacuum, as a small fluctuation of nothing. Now, we know fluctuations exist. I say we measure them in the laboratory. These quantum fluctuations are extremely well studied. For the last 50 years, we can see them doing all sorts of interesting experimental phenomena, like moving plates of metal around, doing all sorts of interesting things. So we know the quantum fluctuations exist. And if the theory is correct, these quantum fluctuations got stretched during inflation, and then grew in a way that I will now tell you about to make galaxies. So remember that dark matter was produced a little bit later on. Dark matter produces gravity, and what it does is that it amplifies these small quantum fluctuations. It makes them grow, as I will show you in this movie. So here's a movie from a computer simulation of the universe, in fact, of a computer simulation of the halo of a galaxy like the Milky Way. So here we see the distribution of dark matter very early on. You see that it's not uniform. These are the quantum fluctuations, or descendants of the quantum fluctuations of the universe, and you're going to see now how gravity causes them to become amplified and to produce interesting structure. So here's the computer simulation, calculating just the equations of physics, and showing us how these tiny little inhomogeneities that we saw, they're getting bigger and bigger and bigger, and producing all these amazing structure. It's just gravity, because if you have a region that's like slightly overdense. Well, it's overdense, it has more mass, it has more gravity, and then it attracts more material to it. And before you know, the universe has evolved into this very beautiful, wonderful, complex structure called the cosmic web. And if you look at some of these lumps, then you see how they get attracted to one another by the force of gravity. And here's some particularly interesting phenomenon is going to happen there in the center. You see these lumps coming together and fusing and building bigger and bigger objects. All that's happening here is the force of gravity produced by dark matter amplifying these quantum fluctuations from inflation and producing an object that will become the halo of a galaxy like the Milky Way. I'm going to show you in a little while how the ordinary matter responds to what is going on in the background, in the dark matter. Now, so let me stop this movie. And so what I've told you about so far is something pretty bizarre, namely that galaxies originate from tiny quantum irregularities, highly amplified by the gravity of the dark matter. Now, when I give this lecture, I often wonder, well, what would happen if Einstein walked through that door, or Newton walked through that door, and they heard me speak? They would say, who is this fella? How does he get paid at the end of the month? Einstein was not a great believer in quantum physics. Newton, well, he didn't even know about the quantum world. What would they say if they heard somebody tell them, you know, the galaxies with their 100 billion stars are the remnants of these quantum fluctuations from the beginning of the universe? I know what Einstein would do. That's what Einstein would do. And I know what Newton would do. He said, I'd rather be a musician. Science rocks. Now, however, going back now to the beginning of my lecture, I emphasized that all we talk about in cosmology is based on physics. In physics, rule number one is whatever you say has to be testable through observation or experiment. It has to be experimentally verified. So to be physics, you got to have a way to test whether your ideas are correct or not. And that's why I love being a physicist. I can wake up in the morning, come up with a crazy idea, and I will still get paid at the end of the month, so long as my crazy idea is experimentally testable. That's what makes science so great. And that's why, in my mind, science is a really high product of human intellect, because we have this rigorous methodology that it must be testable. Now you might say, well, yeah, sure. How are you going to test stuff that happened 10 to the minus 35 seconds after the Big Bang? You must be joking. We're not going to go there. We have no way to see what's going on. Well, we do. Now, the early universe was very hot because all the mass in the visible universe, for example, was all in a very dense state. And when it's very dense, it's also very hot. So the early universe was very hot. And then, as the universe expanded, it cooled. Just like if you pump a tire of a bicycle and you touch it, you see it's hot because you made the air very dense. And then if you blow the air out, then it cools down. This universe did the same thing. As it expanded, it cooled down. In fact, when the universe was 350,000 years old, then it had cooled enough that the plasma that existed before then, plasma is a form of gas where electrons and protons are decoupled from one another. The universe was now cool enough that atoms, hydrogen atoms, could form, and then the electrons bound with protons to make hydrogen atoms, and the electrons had caused the early universe to be foggy. So when these first atoms formed, the fog of the Big Bang lifted, and radiation was free to escape. Now, 350,000 years is very, very early, because the universe is 13.7 billion years old. So scaling to a human lifetime, 350,000 years is the equivalent of 1 day in the life of a human. So when the universe was a human equivalent of one day old, the radiation, the heat from the Big Bang, was then free to escape. And of course, this is the first light of the universe. And if we could see it, well, I'll tell you what happens if we can see it. So the heat of the Big Bang was liberated, if you like, at this early time. And it has been cooling as the universe expands. And today, even though it was very hot at the Big Bang, this radiation by today, because the universe is so old, would have cooled to a mere 2.7 degrees above absolute zero. So it's not at zero temperature, but it's almost zero. It's 2.7 degrees temperature above absolute zero. So we know that, and this was predicted, in fact, by a person whose picture I will show you in a minute, and others many, many decades ago. But in 1964, these two gentlemen you see here, Arno Penzias and Bob Wilson, who were two engineers working in communications, and they had built, they worked in radar during the war, but now the war was over, so they turned their attention to the cosmos, and they were interested in measuring radio waves from the sun. So they were radio astronomers, early radio astronomers, and they built that telescope that you see behind to study radiation from the sun. But they were really annoyed that when they were trying to calibrate their instrument by pointing it away from the sun, they always had a signal. So no matter where they pointed the telescope, they were detecting something. And they were extremely, extremely annoyed that they could not get rid of this residual noise, as we call it in physics. And three people, they were in New Jersey, and in the Bell Laboratories, as it was then, doesn't exist anymore, but in any case, a few miles down the road in Princeton, three people, Bob Dickey, Jim Peebles, whose picture I will show you in a minute, and David Wilkinson, had already understood what this residual heat was. And they were actually building a telescope when, quite accidentally, Bob Dickey, who was the head of the group, learned about what Penzias and Wilson had found. He went back to Princeton and told Wilkinson and Peebles, called them for a meeting, and he says, "Boys, we've been scooped." What these people had discovered, unwittingly, was the expansion of the Big Bang. They had discovered the heat left over from the Big Bang, for which, of course, they got the Nobel Prize. That heat that was bothering them, a signal that they could get from everywhere, was just the residual radiation or heat left over from the Big Bang at a temperature of 2.7 degrees above absolute zero. And we call that the cosmic, because it comes from the cosmos, microwave, because it's so cold that it's in the microwave part of the spectrum, and background, because it's a background radiation. This is wonderful news for cosmologists, because this background radiation that we now detect routinely, and that is the first light in the universe, and it brings us news about what was going on in the universe at that early time. And there are people in this audience who spend their lives understanding the details of this microwave background radiation. Well, what are the news that we get from the Big Bang? Well, this is what I was telling you about before. These quantum fluctuations from inflation are amplified by gravity, and they grow. So by the moment the first light is emitted, these small ripples have now grown, because you saw in the movie gravity amplifies them. They're still quite small, but they are ripples or perturbations or fluctuations that affect not just the density of matter, but also its temperature. And so it was predicted in the 1980s that this cosmic microwave background radiation should not have a uniform temperature, but it should show very, very small deviations from uniformity at very, very small, of 1 part in 100,000 or so. So these predictions were then that the radiation should not have a uniform temperature. It should have slight differences in temperature from one place to another. And in 1992, in fact, April 22nd, 1992 was a very important day for cosmology. A NASA satellite called the COBE satellite that had been launched in order to study the temperature of this microwave background radiation, published this map. Now that's a map of the temperature of the radiation. It looks strange because it looks like a football, like an American football. It's a map because the sky is all over around us. So in order to make a picture of it, we unfold the sky and plot it on a sheet of paper. But the main thing is that the temperature is not uniform. So what you see there is a map of the temperature, and it has a pattern of hot and cold spots. Now this was a really revolutionary discovery that changed our whole view of the universe. It was reported on the front pages of newspapers as they existed then. This is a British newspaper. I got the date slightly wrong. It was the 24th of April, not the 29th. Now I hope you'll forgive me. I'm going to leave modesty aside for a second, because I did make a contribution that was reported here on the front cover of the newspaper. You probably cannot see that, but I can. And it says here, says, "Oh, wow. You have no idea how exciting this is." Carlos Frenk, an astronomer at Durham University, said yesterday. So this was my great contribution to cosmology and my great contribution to this big discovery. For the dean, the next sentence says, "All the world's cosmologists are on the telephone to each other at the moment trying to work out what the numbers mean." Now, telephones in those days were really expensive, and I got a phone call from my dean saying, "What were you doing using the telephone talking to all these people in the US?" That was my contribution to cosmology. My wife knows my epitaph on my grave will say, "Oh, wow." And that's what it was. And now that wow discovery earned my good friend George Smoot the Nobel Prize in Physics in 2006. 10 years later, this was measured again with much better resolution by a satellite called WMAP. For W, you remember I talked about Peebles, Dickey, and Wilkinson. W is Wilkinson, the boys we've been scooped, one of them, who sadly designed the instrument and died just before of cancer at a very young age, just before this picture was published. The Europeans always like to run behind the Americans, but you know, they like to run behind, but when they get there, they do better, and the Europeans finally got their act together, and the Planck satellite remeasured this radiation with now much greater accuracy a decade later. And that is so this, what you're looking at here, if the theory I've been telling you is correct, are quantum fluctuations from inflation. And how do we know that's what it is? So this is the only graph I have in this lecture that has complicated things. I'm not going to explain the complicated things. What this graph is a mathematical description of that pattern of hot and cold spots. For the most interesting people, what it measures is the difference in temperature between 2 points in the sky as a function of how far apart these points are. So the main point is that it's not a trivial graph. It has all sorts of interesting structures that we understand with physics, and these predictions were made by Jim Peebles. There were 3, Dickey, Wilkinson, Peebles, so that's the Peebles, and Jim Peebles. And so that were the predictions for 1982. Now this is the situation after Planck. And this is one of the most important plots ever. To me, I've shown this and I've talked about it, and I've taught and lectured hundreds of times, and I still cannot see it without feeling my knees shake, because it really is quite an incredible plot. So what you see here in green are the predictions from Peebles and others from the 1980s for how these, how inflation and these quantum fluctuations would modify the radiation of the Big Bang and produce this pattern of hot and cold spots that you see there. So that's what the curve means. The dots are the measurements by Planck. And as you can see, they fall exactly where the theory predicts they should fall. So to me, I think physics doesn't get any better than this. So why is it that in this little corner of a galaxy, a species of animal has evolved that on the one hand has the capability of making theories about how the universe began, it's the green line, and this same species also has the ability to build machines that they launch out of their atmosphere capable of measuring signals that are 1 part in 100,000 strong. So to me, this is a tribute to the greatest side of humanity. I think this is the physics equivalent of a Beethoven symphony or a Rembrandt picture, but it's better because Beethoven and Rembrandt were individual geniuses. This is a result of the effort of thousands of physicists and mathematicians working in order to produce this tremendous advance. So I said life doesn't get any better than this. My wife objects when I say that, but I think it is true. Certainly physics doesn't get any better than this. But what does this mean? Well, this means, oh, by the way, here's a picture of Jim, my inspiration of all people in my generation. Finally, they gave him the Nobel Prize in Physics in 2019. He should have had it many times, and the Nobel Committee realizes, if you read the citation, you don't know what they gave it to him. Why? Because he did so many things, each of which deserved the Nobel Prize. So they gave it to him probably for the predictions for this plot that I just showed you. Now, so I'm nearly done, and, but what the significance of this is I told you, we have this crazy idea that galaxies came out of quantum fluctuations in inflation. Here is the empirical evidence. Here is why I can stand here and give the Misel lecture telling you about this development. Here is the evidence. Here is what makes physics so special. Now, so just to finish off, you say, well, wait a minute. We're only down to 1 day human equivalent in the life of the universe. We still got the next 100 years to go. Well, we do, but I'm going to be very quick because I'm mindful of the time. How is it that those small irregularities grow into galaxies? And here, in fact, how exactly did galaxies form? The problem here is a lot simpler. And it is a lot simpler because we have this amazing new tool of science called computing. So big computers extend the human brain in ways that was unthinkable even when I was a student. And because we understand the physics, we can simulate in a big supercomputer the entire cosmic history. What you need to do is you need to know how the universe began, which we know. The initial conditions is this pattern of hot and cold spots. You need to make some assumption about the universe, that it has so much dark matter, so much dark energy. And then the rest is just solving 100-year-old equations or more, the equations of the physics that are relevant to the problem. And now computers are very good at solving equations, and in fact, they're much better than students. I can see probably some students here. So I'm sorry to tell you that the computers are a lot better than you are for a number of reasons. One is they work on weekends. They never complain. They don't give you a professor's report at the end of the calculation. And most importantly, they always get the right answer. So we can now then simulate the entire evolution of the universe, and we program a computer with the equations of physics, and we go away and come back and see what happened. And I'm going to show you just 2 movies to finish off. This is what you would see. It's called the Millennium Simulation. Any of you who likes it, you can download it from the web. This is a journey of what you would see if you were able in the universe to see the dark matter. What you see here is only the dark matter. And you were able to travel at many, many times the speed of light, you would see this amazingly complex, beautiful pattern, the cosmic web again, of filaments that intersect and make big blocks of dark matter, which with the galaxy clusters form, and a very, very rich universe, all coming through gravity from these quantum fluctuations of inflation. Now, over the last 6, 7 years, there's been a breakthrough in that we're now able to simulate not only the evolution of the dark matter, but also the evolution of the ordinary matter in the universe. So what we're going to see in a second is how the gas, the ordinary matter, responds to the gravity of the dark matter. So here you already see gas, and now we're going to no, this is the gas, sorry, before it was the dark matter. This is the gas. We're going to zoom into a region of particular interest. This might remind you of the movie I showed you earlier, because the gas has collected into these lumps of dark matter. They produce the gravity, and they bring the gas along. And when these blobs of dark matter collide and fuse together, so does the gas. But the gas can spin, and you see these disks. And now we cut to stars, these disks of stars that came out of our computer. The evolution continues, and the galaxy gets bigger, and we know why things spin in the universe, and then here's gas again, and we are going to, in a minute, go back to stars, and you'll see that something quite interesting came out. And all that comes in here is these quantum fluctuations of inflation and the laws of physics, and that's what the computer produced. We're now going to zoom out, and you will see that this was happening everywhere in the universe. Many galaxies are forming, so now we have the ability to simulate not just dark matter, but also the visible part of the universe. And these are images. If I just show them to amateur astronomers, they'll say, well, which page of the Hubble Atlas did you get this from? No Hubble Atlas. These are galaxies produced by a computer. So these are what comes out of our computer simulations. And those of you who've seen an image of a real galaxy, well, if you're professional astronomers, you can immediately tell that these are fake, but, or not fake, they're artificial. But if you're not an expert, they look very, very convincing. So let me just conclude with what I've been telling you tonight. We have, over the last, well, in my lifetime as a scientist, and I'm not that old, gone from a state in which we knew nothing about the origin of galaxies to a comprehensive theory of how our structure, how our universe was made. The story begins very soon after the Big Bang, when the universe inflated, and that inflation produced these small fluctuations amplified by cold dark matter that are reflected in the pattern of hot and cold spots in the microwave background radiation, which seems matches exactly what the theory predicts. We then have computer simulations that allows us to go from there to the universe of galaxies. So what about the future? Well, I like to talk about the future by reference to one of my favorite pictures. It's a triptych by Hieronymus Bosch, a 15th century Dutch painter. And like all triptychs, it has three parts. The center represents, it's called the Garden of Earthly Delights. The center is Earth. And here you can see all sorts of earthly things going on. So here on Earth, I put the question of what is the dark matter? I think that's an earthly question, one that, as I said, is going to be answered in the next 5 years, and that's just perfectly normal. On the right is hell. Now, I reserve hell for dark energy. It's a hellish concept, is one, I don't know if Keith Olive here will agree with me or not, but our generation, Keith, I think he's somewhere here, I think he will agree, our generation is not going to solve this problem. The next generation might, and I really wish I could live long enough to see the next generation and see if they can tackle this problem. On the left, there's heaven. So I left for heaven the heavenly question of how did the universe begin? So that we know there was a Big Bang, but as my mentor Martin Rees likes to say, we don't know what went bang. And I think that's a perfectly appropriate question to put in heaven. And anybody who answers it, no doubt, will have a good claim to being in heaven. Now, so humanity, for reasons that one might want to speculate about, has decided to spend billions of dollars building instruments to try and answer these questions. Here are some that one you will definitely recognize is JWST. My slide's a bit old. It says the next space telescope is the current space telescope, as no doubt everybody here knows. And there are several of those instruments in the US, in the case of JWST and LSST, in Europe, in Euclid, in China, there's a telescope called FAST, and also in the US, there's this wonderful instrument called the Dark Energy Spectroscopic Instrument. But above all, we have human ingenuity, the human mind, whose power nowadays we can amplify many times through the power, computational power of computers. Somebody told me the other day that my computer in Durham is now capable of doing as many operations as a human brain can, and my computer is just getting bigger and bigger and bigger, where the human brains are not. So that is what gives us optimism. So I conclude with a picture of my cathedral, not mine, but the Cathedral of Durham, and we have really seen tremendous progress in understanding the universe in the past 40 years, but I think a lot of the best is still to come, and I'll stop here.
So we have some time for questions, and we have microphones to be distributed. So if you wish to ask a question, please raise your hand. Before that, let me mention that Professor Frenk will give physics and astronomy colloquium tomorrow at 3:35 in Tate Building at the campus. So you're welcome to come and to listen for another beautiful lecture. And another thing is that you have questionnaires at your seats. So please fill them as good as you can, so that will help us to improve our delivering the lecture series. So questions, please. Megan, do we have mics? Yes, mic is there.
Hi, I'm with the Minnesota Astronomical Society. I've heard the Milky Way galaxy is about 10 to the 12th power solar masses. What percentage of this might be dark matter?
Right. So so you're absolutely right. The mass of the Milky Way is 10 to the power 12 times the mass of the sun, and 90% roughly of that is dark matter. The rest are the stars and the gas, which makes a comparable contribution to the stars. So the Milky Way is essentially, in round numbers, 90% dark matter and 10% stars and gas. And those numbers we know very, 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 very accurately. We know them to a precision, I would say, of 10% or so.
Am I on? Can you hear me? Oh, see, we got two short time frames: the quantum fluctuation time period and the inflation, time period. So there must be some relation between those two. Like if the fluctuation was too short, the universe couldn't have had. Does the fact that the universe exists imply some relationship between those time frames?
Sorry, the fact that we...
The time frames I'm talking about are the time frame associated with the quantum fluctuation,
Yeah. So
and the time frame associated with the inflation.
Right. So I think the time scale for the quantum fluctuations is very short compared to the expansion time scale, which is of order 10 to the minus 35 seconds. Keith can correct me if that's not.
And what's the fluctuation time scale approximately?
Keith knows the answer to that.
They're about the same.
Comparable.
Right?
Yeah. Yes.
The same scale, it's the same physics.
Right.
It's the same time scale that causes.
Right. Because it is, so that's what Keith is telling us. So he works on this kind of stuff and other things. But because it's the quantum field that's driving the inflation, and it's the vacuum energy that's driving the inflation, and the fluctuations are part of that quantum field. So they are the same phenomenon in a way.
The problem is getting out of inflation, right? So
Yeah.
once you're in an inflationary state, it's,
How do you get out of
hard
it?
to get out of it, and that's where then the fluctuations come from.
Right.
So I have a naive question. Do we need to invoke dark energy and dark matter? Couldn't we tinker with the form of gravitation law that becomes repulsive at large distances?
The form of gravitational law that is not like Newtonian.
Yeah, that becomes repulsive at long distances.
Well, repulsive, right.
Yeah.
So, okay, so there's many dimensions to your question, so it's a very good question. Now, so could it be that there's a link? So let me simplify your question. Could there be a connection between dark matter and dark energy? Could they be different manifestation of the same unknown physical phenomenon? Can I rephrase your question like that? I mean, you were very specific, but I think underlying your question is that, could there be the same thing? And we just simplified and separated this into two problems. Can I simply, well, so I think the answer for that is, of course, we don't know. Now, there are models where the two, dark energy and dark matter, are indeed a manifestation of the same underlying physical processes. And so these are models where the same sort of physics produces on large scales, on very large scales, the repulsive force of causing the expansion to accelerate, but can also produce a gravitational force like dark matter produces. So there are theoretical attempts to unify the two. I would say that there are not many people working on that because there is not any clear way in which you could test that sort of ideas. But there are certainly possibilities that we may just be blinded. We may be like physicists were at the beginning of the 20th century, where they can recognize that, for example, the speed of light had to do eventually with the whole structure of the universe, and there were all sorts of phenomena that were distinct and then became unified with relativity or with quantum physics. So we could be in a situation like that, and our descendants might laugh at us and say, why were these people naive talking about dark matter and dark energy when we now know there's whatever it is. So that's certainly a possibility, but there are, as I say, people working on that, but not yet making any sort of convincing progress in that way of thinking, but it's definitely not ruled out. And all this investment that I mentioned of billions of dollars in new instruments, it's quite interesting. They are advancing the empirical side of the subject, trying to make measurements with enough precision that they would begin to constrain theories about dark matter and dark energy. And who knows, 10 years from now, the answer might turn out that we're just being very naive and there's something much more profound that unifies the two. Yeah, so yeah, thank you for that question. But at the moment, it's just speculation.
I have three ignorant questions. One, what was there before the Big Bang?
What was it before the Big Bang?
And two, what caused the Big Bang?
What caused the Big Bang?
And three,
yes.
Will we ever have a telescope powerful enough to see deep into the universe so that we'll see real close to the time of the Big Bang? Right.
Thank you, Bianca, for those very interesting questions. So the first two are similar. So what was there before the Big Bang and what caused the Big Bang? When I was a child, the age of Alex's son over there, I asked that question of a Nobel Prize winner. I won't mention his name because he almost put me off studying physics by the answer he gave me. He said, oh, look, time is part of the universe, so it doesn't make sense to ask what was there before time. So asking the question, what was there before the Big Bang, it does make sense because there was no time. I nearly decided not to be a physicist when he gave me that answer. It was a completely wrong answer to give. I think the question is extremely well posed. The answer is we don't know what caused the Big Bang or what was there before the Big Bang. So we know there were, as Martin Rees says, there was a bang. We just don't know what went bang. Now, there are efforts to try to answer that question within physics. For example, by the way, I remember, I said Andre Linde thought about inflation. There was two people, Andre Linde in Moscow, and then Alan Guth in MIT. I remember Alan Guth came to give a lecture in my university, and I remember I drove him back to his hotel, and then suddenly we say, Alan, it's 4 a.m., and we were just talking about that question. Alan had something that I clearly didn't grasp, that's why it was 4 a.m., of something, some sort of fluctuation of something that created the universe. So we don't really know, it's very speculative. But there are very famous people, Roger Penrose, for example, who's a Nobel Prize winner, a very old mathematician in Oxford, who thinks that, in fact, there's still the universe goes through many phases of Big Bang, and there's a way that you could transition between one bang and the next. He makes some quite elegant arguments, and moreover, he came up with some potential tests of the idea that there isn't just one bang, but a universe that keeps repeating, going through phases of Big Bang, and then emerging again, essentially indefinitely. So there are efforts. He's one. There's another person also in the UK, somebody called Neil Turok, who also has some arguments as to how we might, in fact, see past the Big Bang, and what lies behind the Big Bang is another universe. And so there are efforts to try and answer these questions. They're very profound questions. Now, the reason that I'm somewhat skeptical, or who am I to be skeptical of Roger Penrose's ideas, but the reason I'm skeptical is because we do know one thing. We know the limits of physics, and we know where physics breaks down. So, in the 19th century, before quantum physics was invented, well, quantum physics was outside physics. You couldn't ask questions about atoms. You could ask them, but you couldn't answer them because we didn't have the background and the tools. Now we know where our tools break down, and we know that they break down not at 10 to the minus 35 seconds, but a little bit earlier, something we call the Planck time. And the reason we know the breakdown is because we have two big branches of physics: relativity, Einstein's relativity, and quantum physics. Now, in this world, you can talk about the two separately, because relativity refers to the whole universe, quantum physics refers to atoms. And the atoms don't care about the rest of the universe, and the universe doesn't care about atoms. However, at the Big Bang, uniquely in the history of the universe, quantum physics and gravitational physics are equally important. So the universe is so dense that the strength of quantum forces, and it's so dense that the strength of gravity is comparable. And so you need to talk about the two together. You need something that we call a theory of quantum gravity that Einstein tried to develop and failed. Stephen Hawking spent most of his life trying to develop quantum gravity and failed. And so, in my mind, it's wonderful to see Roger Penrose speculating, but at the moment it's no more than speculation, because the physics tools that we have just break down. We don't have the right theory, and so you try to do something and nothing really makes much sense. So, of course, there are efforts of theoretical physicists trying to bridge this gap, and there are advances in theories of quantum gravity, but we don't have an accepted theory that would allow us to answer what I think is the key question. That's why I put it in heaven. What created the universe? I think we don't have the tools yet, but maybe in the future these tools will emerge, and then we can answer that question. I think there are two really big questions. One is that one. The other one is, are we alone in the universe, or are there more intelligent life somewhere else? To me, those are the two most interesting questions that I'd like to see maybe answered in my lifetime. And we may answer at least one of the two.
Hello, question here.
Yeah.
Oh, sorry. Getting back to the future as opposed to the beginning of time, you knew a question about the James Webb Space Telescope was bound to happen. Have you looked at some of the most recent images that have been released over the past couple weeks or so? I think it's not a conclusion yet, but it's an impression that some of the images taken that should show the earliest galaxies forming somewhere earlier than 300 million years after the Big Bang are showing galaxies, but they're both showing more galaxies than expected and more highly developed galaxies than expected. I was wondering if you have had any chance to think about that.
Yeah, well, I think I have to be polite nowadays. So I'll be polite. Now, how can I be polite? I think, all right, so let me say, there was a flurry of papers. As soon as the data were released, the papers were already written, they just fill in the numbers. And then these papers were published, including the ones we're talking about. And 3 days later, the JWST team said, we had a calibration error in the data, right? So I think all that stuff's completely premature, and it's certainly wrong. I think, I was trying to be polite, so let me not be polite. I think it's just wrong. I think the data, as I say, changed. They were analyzing incorrect data and analyzed it in the wrong way. So I personally don't put any emphasis in those statements from otherwise very reputable physicists. One of them, a friend of mine, who actually was in Minneapolis moonlighting here because his wife was here. Anyway, I won't mention his name, but I think he put out one of those papers and they're just not right. I mean, that's just, that's the way science works. Science has to be ready to be wrong. So if you not risk making incorrect statements, then you don't advance. But I think in this case, rushing to write papers before the data are fully understood was really taking a risk too many. And I hope the reputation of my friend survives. I wouldn't pay any attention to those results personally. Right.
Yep, my question is, where did the gas come from?
Where does the gas come from? Right, well, that's a really very interesting question. So the gas is essentially the ordinary matter that I talked about. All of it was once gas. Now, where does it come from? And why does the universe have dark matter and gas, or ordinary matter? I don't think we really know where it comes from. It comes, the person behind you was talking about getting out of inflation. And so when the universe comes out of inflation, then there's this energy left over that somehow transforms into matter. And so it has to do with these very early phases in the universe. It has to do with energy left over from this very early phase, but exactly how it turned into matter and how and why are there two different forms of matter, one that is dark, the other one that isn't dark. That's not clear at all, but it does go back to the very early phases of the Big Bang, where some energy, because energy and matter are the same thing, right? That's what we know. I don't know if you've already come across E equals mc squared at your young age of 9.
I have, actually.
Right, so the early universe has lots of E, and then some of it turns into M. And so exactly how, I think it's not totally clear, but it's to do with the physics of the very early universe. But yeah, it's a very good question. So when you become a physicist, Andre, you might answer that question yourself.
Okay.
And then there's another interesting question that maybe you'll answer. So in most of, why is the universe made of matter and not equal amounts of matter and antimatter, where you would expect, everything to be kind of democratic, and we live in a universe that has matter and only basically no antimatter. So that's a big fundamental question in physics, which is related to your question, and we don't know the answer. So there are many, many open, interesting questions for people like you, if you do become a physicist, to answer in due course. And this is one of them. And the one that Bianca answered is another one.
All right. We can continue privately here at the podium for a few minutes more. But for now, let's thank Professor Frenk again.